Okay, so let's talk a little bit about the actual eye and vision in more detail. So we'll talk a bit about kind of the basics of vision, how your eyes work, properties of light, and then we'll go into actual perceptual organization, grouping principles, and monocular cues. So vision is, of course, the most complicated but also the most important of our senses, okay? So before going into the structure of the eye, though, let's talk a bit about light and kind of what properties determine how we perceive color. So light travels in waves, basically, and that's exactly what it sounds like and kind of looks like. So kind of these like waves in the ocean, right? Light travels kind of like that in terms of waves. And properties of these waves are going to determine what color we perceive. There's actually two of these though. So one is going to be wavelength, and this is going to determine what color we see. So shorter wavelengths are going to give a different perception of color than a longer wavelength. So wavelength is going to determine what's called hue. Hue is really the proper term. The reason we don't say determines color is because, well, color is a little more complicated than that, which we'll get to in a second. But yeah, shorter wavelengths are going to give us different hues than longer wavelengths. So something to keep in mind, though, is that the actual wavelength spectrum is a lot bigger than what we can actually perceive. Okay, so you see here, you have UV rays, X-rays, infrared, microwave. These are all out of the spectrum that we can actually perceive, right? So it's only this small little bit of the spectrum that's visible to humans. Okay, it gets a little bit bigger for some species. I think bees can see a little bit broader on the spectrum, but not a ton. And like I said, to us, what we can perceive is only a small amount of the whole spectrum. Anyways, back to wavelength. So as you'll see here down below, shorter versus longer wavelengths give us different colors. So shorter wavelengths are purple, blue, medium are green and yellow, the 5 to 600, and the longest wavelengths that we can perceive are going to be perceived as red. Okay? So another thing is that another property of the waves that's going to affect what we perceive is the amplitude. So by amplitude, we mean how high or low are the waves going to travel. So over here is high amplitude. You notice how high and low it goes. Over here is low amplitude. That's going to determine what's referred to as intensity. Okay. So what we mean by hue, just to make it clear, hue is going to be, okay, am I perceiving green, blue, or red? Intensity is going to be, am I perceiving light green, dark green, medium green, right? So make sure you're clear on that. And like I said, amplitude is going to determine intensity, or kind of the brightness of it. Wavelength is going to determine hue, which color, okay? All right, so on to the actual eye. First you have the cornea. So this is kind of the surrounding part of the eye, kind of protects it. You have the pupil. That's of course black spot right here, kind of in the center of your eye. And you have the iris. So the iris is the actual colored part. Okay, so the iris is going to, whether you're brown-eyed, blue-eyed, green-eyed, that's the iris that you're thinking about. But the iris serves a very important function. It can basically adjust the pupil, so the muscles in the iris can contract or release to a certain degree in order to alter the size of your pupil. So if you've ever looked at someone, say, or maybe you've noticed this in a cat, if you have a cat, that's where I often see it. If it's really bright out, their pupils get really narrow, right? They're just like a little slit. When it's dark out, their pupils are quite large. And it's more pronounced in cats because I think they have a bigger spectrum of vision. They can see better in the dark, but it's the same with people. Right? If you step outside, it's really bright out, your pupil is going to be quite small. If it's fairly dark out, your pupil is going to be bigger. And this is controlled by the iris. So you can think of the iris as kind of pulling the pupil open if it's dark, or kind of squeezing it a little bit, making it more narrow if it's quite bright out. And this serves a function because this is going to determine the amount of light we can actually take in. So if it's really bright out and it's kind of maybe too bright, your iris is going to kind of compress a little bit because you want your pupil to be narrow so you're not taking in as much because it's so bright, it's kind of blinding you. If it's dark and it's hard to get enough light, pupil is going to kind of open up a bit because the iris is going to kind of almost open. Okay. Then you have the lens. And sorry, so the pupil, that's like I said, or kind of alluding to, that's where the light is going to enter from. Okay? So iris is going to control how open it is, but the actual light that's for vision, or really is vision, is going to go in through the pupil, okay, through the little black part. And this is all, and then it's going to go through the lens. So the lens is super important because the lens is going to be basically altering the light. It's going to kind of bend it, and it's going to bend it so it can be kind of more or less focused depending on how far away it is. So this is something another thing you'll cover a lot more in higher level perception courses, but the lens is going to kind of bend the light so that it can be focused onto the next part, which is going to be the actual retina. Okay. So the retina, this is kind of where the magic happens. The retina is where things are stimulated, basically, or sorry, where the light kind of almost stops doing its thing. The retina is what takes in different lights and then kind of stimulates the optic nerve. Okay, so just to say again, it's going to go through obviously your cornea. Your iris is going to open or close your pupil a little bit depending on the situation. Light goes in through the pupil to the lens. The lens kind of reflects, or not reflects it, but bends it and sends it to the optic nerve. And then, the retina, the lens is going to bend that light so it goes to your retina. The retina is going to receive it and then stimulate the optic nerve. Okay. Okay. So the retina contains several different, so like we said, the retina is where the light ultimately ends up before stimulating the optic nerve, and then transduction happens, which we talked about earlier. So the retina is going to contain what we call photoreceptors. And these are basically things that are going to receive that light and then are going to end up stimulating the optic nerve, where the rest is going to be, then it's going to kind of go all the way to your visual cortex, occipital lobe, and that's how you see, basically. But like I said, before all that electrical stuff happens, the retina is going to need to receive that light. Okay? So the retina actually contains two different photoreceptors. One is going to be called rods, and one is going to be called cones. Okay? I don't want to say that a word, but so the cones are basically going to be clustered around what's also called the fovea. So this is going to be more central in your vision. So if I'm looking say right at the center of the screen here, where the mouse is, that's kind of where, that's where your fovea is, okay? It's going to have more cones there. So the photoreceptors that are going to take in kind of what's right at the center, what's really at the center of your vision, that's going to be primarily cones, okay? However, outside of that, kind of in your peripheral vision, so if I'm looking at the screen here, my hand over here is going to be in my peripheral vision. So not what you're looking directly at. That's going to be made up of rods. Okay, or at least more rods. But the difference between rods and cones, well, there's actually a few. So we talked about location. So again, cones are going to be more clustered around your fovea, kind of the center of your vision. Rods are going to be more your peripheral vision. But they also differ in a few ways. So the cones allow us to have color perception, okay? So rods really only see in black and white, but cones can see in color. I mean, the whole thing is seeing, but just if you want to simplify, think of it in a simple way, the cones are about color perception, the rods are black and white. However, the cones actually have disadvantages. So the cones are going to be less responsive to dim light, okay? The rods, on the other hand, we already talked about their location, are only black and white, but they're important for peripheral vision, and they also tend to be more responsive to dim light, okay? So if you're actually looking for something in a fairly dark scenario, so say you're looking out into a forest, you're better able to perceive it if it's in your peripheral vision when darkness is the issue. That's because, again, the rods are more involved in peripheral vision. The cones are more central vision. So with that in mind, because the rods are more receptive to dim light, they can perceive things. Your peripheral vision is actually better for perceiving kind of dim light objects. Anyways, so keep that in mind. There's the rods and the cones, and they kind of each have different functions and specialties. Okay, so on to actual color processing. Well, what color is this tomato? We, of course, perceive it as red, right? But the tomato itself is not red in a sense. It's actually everything but red. It's reflecting red light, or wavelengths that allow us to perceive red. So it's not exactly that the tomato is red, it's only that we perceive it as red because it's reflecting a certain wavelength. Okay? So in other words, color is kind of a mental construction, right? This is all just wavelengths, amplitudes, but we perceive that as color, okay? Okay, so color vision is a really cool thing we can do, something we obviously don't need to think about, but it's not surprisingly fairly complicated and not 100% understood. But nothing's really 100% understood, especially not in psych. So this is the theory. If you've ever painted, you'll know that you can create pretty much any color from the three primary colors, right? So if you have red, green, and blue, you can easily make any color, right? Pretty much any color. Well, except for gray, but anyways. You can make purple by mixing red and blue, right? You can make yellow by mixing red and green. So if that's the case, if we can make any color from these three primary colors, the theory was, well, I guess still is, that maybe our receptors are basically tuned the same way, right? So maybe we only have red, green, and blue color receptors. And that does seem to be the case, right? So there's lots of evidence that this is the case, that perceiving something like yellow, there aren't actually any yellow receptors, right? There also aren't any purple receptors. What you perceive as purple is really just a mix of red and blue receptors getting activated, right? When you perceive yellow, it's just both red and green receptors being activated. There's no actual yellow receptor. And like I said, there's a lot of evidence for this. We won't really go into that. However, trichromatic theory can't really account for all findings when it comes to color. There's a couple things it has a tricky time explaining. So one finding is that when you look at people who are colorblind to red, okay, so they have no red receptors, they can still see yellow, which doesn't make a ton of sense, right? So if yellow is just a combination of green and red receptors working, if they have no red receptors working, they shouldn't be able to perceive yellow, right? They should just see yellow as green, but they still can see yellow for some reason. So this led to another theory, one called opponent process theory. One more thing though. Another thing that trichromatic theory has trouble explaining is the nature of yellow in general and why it's different from purple. So by that I mean that purple does kind of look like a combination of red and blue, right? Yellow doesn't really look like a combination of red and green. It looks like its own color. So with that and the fact that red blind people can see yellow led to this other theory called opponent process theory. So this is the idea that basically things work in opposition to each other. And we'll get to the evidence for this in just a second. So when you see something red, what's happening is that basically there's receptors for red that are going to stimulate and activate neurons associated with red, whereas it's also going to basically nullify or decrease, kind of turn off, you could say, activation of green neurons. Okay? And the opposite is also true. When you see something green, not only is it going to turn on green neurons themselves are not green, but I mean the ones responsible for green. When you see green, those neurons responsible for green are going to be activated, but it's also going to deactivate red neurons responsible for red. Okay? Same goes for yellow and blue and white and black. So you see one color, it doesn't only activate neurons for that color, but it also is going to deactivate ones for the opposite color. So yellow is going to deactivate blue, black is going to deactivate white, and so on. So what exactly is the evidence for this? Well, I'll let you do this on your own if you want. It's pretty cool, but since it takes a few minutes of staring, I'll just explain what typically happens. So if you get people to stare at this for like a few minutes, and then if you get people to stare at this for a couple of minutes, or maybe 3 minutes, next what you do is you show them a white screen. They'll report seeing the typical American flag, right? So the yellow will, when they see this screen, make them see blue, black will make them see white, blue will make them see red, right? So after they're staring at this for a while, they will see the normal American flag. Well, this has been used as evidence for this idea of opponent processing. So the theory is what happens is, well, we'll go through each color one at a time, but staring at yellow for a few minutes is going to basically exhaust, it's going to tire out all the stuff involved in perceiving yellow, right? When you get to this one, it's all white, and white is actually a combination of all colors. White contains every color, including blue, right? So because your yellow system is exhausted from staring at yellow, that allows the blue system to kind of be overly active. You can think of it that way. So we say that again, because your yellow system has been exhausted from staring at this, blue, which is in opposition to it, is able to become more active and take the blue out of this white, right? And it's of course the same for the other colors. So if you've been staring at blue for 3 minutes, when you see white, your blue system is exhausted, it's tired. Red, which is in opposition to it, is basically gonna be more active because it's not tired, okay? And that allows you to see the red within the white. And of course the same for black, because you've been staring at black, this is going to wear out, tire your black system, and it's going to allow you to see the white. The white is already there. So that's this. Another thing we mentioned earlier, so yellow doesn't really look like a combination of green and red, whereas purple does look like a combination of red and blue. So the theory here is that because red and blue work on basically different channels, you can kind of see both at the same time, right? And that's why purple looks like a combination of red and blue. Whereas red and green work in different, work in the same channel. So they can't really both be active at the same time, okay? So that's why yellow looks like its own color, not so much a combination of red and green. So like I said, kind of the full details on opponent process theory are a bit beyond what we can cover here. It's a pretty complex theory overall, but that's kind of the gist of it, right? Things are working in opposition. So just remember that part of anything. Okay, so let's move on, talk a bit about perceptual organization. Oops. So with perceptual organization, start out by having a look at this thing on your left here. So what do you see? You probably see a cube, right? Pretty much everyone sees a cube there. So this is kind of meant to illustrate this idea of Gestalt psychology. And it emphasizes our tendency to integrate pieces into a whole. So rather than seeing a bunch of separated black circles with white lines through them, we tend to group them and kind of organize it in a way that we can see something more meaningful, that being the cube. And there's three principles we'll talk about here. One being our grouping principles. One we'll talk about is proximity, where we tend to group nearby figures together. So because of this space, we tend to see this one set of black squares and this one set of black squares, rather than seeing one bigger thing of more black squares. Another one is continuity. So looking behind here, you probably think it's kind of spoiled there, but two sticks crossing, right, like that, behind the tree. We tend to not think that it could be this, right? Two kind of weirdly shaped sticks that go like that. The reason is that we like to kind of implicitly assume continuity. So rather than just assuming the sticks are weird, or maybe even that there's 4 sticks, we like to think of things as going in a nice continuity driven way. So the stick is just going to continue going this way behind the tree, and the other stick is going to be continue going this way behind the tree, right? We pretend to perceive smooth, continuous patterns rather than discontinuous ones. So another example is, let's say you looked at a pile of rope that was kind of all tangled up. You would probably kind of implicitly assume that that's just one long rope, really tangled, rather than a bunch of different ones, because we want to kind of see it as continuous. And the last one, closure. So we tend to fill in gaps to create a complex object. So you probably see a triangle in the middle. There's actually no triangle there. This shade of white is no different from this, but because we kind of want to be able to perceive objects, we use closure here to kind of assume that there's a triangle. And just as kind of a side note, so I talked a long time ago in the first lecture about Sigmund Freud and kind of how the unconscious theories are sort of still around. This is what I'm talking about, right? So all the stuff about like, you know, symbolic dreams and unconscious desires, that's kind of not so much a thing anymore. But basic ideas about kind of unconsciously how we organize things, how unconsciously we perceive continuity is very much alive and well. Just a little history right in there. Okay, so moving on, we of course have the case of depth perception. You can easily imagine why depth perception is important. It enables us to estimate an object's distance from us, something we use literally all the time. Well, when it comes to depth perception, there's actually two ways we perceive depth, or two kinds of ways at least. One is what we call binocular cues, and one is what we call monocular cues. Okay, so what happens with binocular cues is both eyes, of course, have a retina, right? And both of them are actually going to get different images. So seeing from your left eye versus your right eye, you're of course getting kind of two slightly different angles looking at the same thing. As a side note, how our brain actually manages to kind of create mold those into one single image is kind of a mystery. We're not totally sure about that. But anyways, the fact that both of your eyes actually are able to perceive different images is what creates binocular cues to depth perception. So by seeing two different images, we can basically make out what's farther away from what. So that's kind of why we have two eyes, right? It allows us to see depth using binocular cues. That's not something we're going to go into more, but just remember that part, that the contrast between the two different images your eyes are getting is allowing you to see depth in that way. However, this is not the whole story, right? Although we can see depth using binocular cues, like the contrast between our two eyes, we also use what's called monocular cues, okay? And these are kind of heuristics, I guess you could say, for judging depth, even when we don't see any binocular disparity, okay, or difference between the two eyes. So let's look at them. Well, the first one is, of course, going to be relative height. So again, we're dealing with stuff here that does not result from a contrast between what your two retinas or your two eyes are seeing, right? This is all stuff we could tell even with only one eye, or if you looked at, say, a flat picture. Well, a big one is relative height, okay? So by relative height, we mean that objects that are higher in our visual field appear far away, okay? So looking at this picture here, the bush and the ducks obviously seem closer than the house because it's higher up in our visual field, right? We use that monocularly to perceive depth. Another one is relative size. So smaller objects, especially when they're the same object, are perceived as farther away. So since we have these two rowboaters or rafters or whatever, the fact that one is smaller is going to tell us that he's farther away, right? And we kind of know that they're going to be about the same size. They're both normal people. So the fact that one is farther away tells us that, or sorry, the fact that one is smaller tells us that he's farther away, right? By the way, just jot these down because we'll do kind of a quick activity. So relative height, objects higher in our field of vision appear farther away. Write that down. Relative size, smaller objects are perceived as farther away. The other one is interposition. also known as overlap or occlusion. This is the idea that if one object partially blocks our view of another, we can also perceive it as closer. So with these two vans driving up the road, the fact that one is partially blocked off by another, of course, tells us that the orange van is blocking off the red van, so that's going to tell us that the orange van is closer to us, right? Same with the tree, because the tree is blocking off the grass behind it. We know the tree, this first tree is going to be closer to us. And another one is going to be linear perspective. So by this, we know that lines that kind of converge or parallel lines that appear to meet in the distance also signify depth. So if you see a train track and the tracks look like they're converging in the distance just by being parallel, this is another cue to depth, right? The last one is going to be texture gradient. So what I mean by this is that texture becomes less and less apparent as objects are farther away. So when you're looking at this ground here, you can see in great detail the texture of it, right? You can see the gaps in a lot of detail and kind of a little bit of sand on there. Whereas you look at the stuff that's farther away, it's really hard to see all that detail, right? The texture is less and less apparent the farther it gets away. So when there's great detail in the texture, that tells us it's closer. When there's less and less, that tells us it's farther. Okay, so let's do a little activity. So 4 of those depth cues we just talked about are going to be here. Let's in this next picture. So I'll give you a second to point them out, and then we'll go over them. It's just the 4. Texture is not here. So remember, linear position, linear perspective, relative height, and relative size. Well, here's the first one, interposition, right, or occlusion. So since this tree is partially blocked by this first tree, that tells us, of course, that this tree is closer. Right? Again, none of this is happening with binocular depth perception. It's not because our 2 eyes are getting different things. This is all monocular depth cues. Okay, what would be the next one? Well, linear perspective, right? Because these lines are actually parallel, but they look like they're converging, that tells us that there's an increase in depth, right? Next one is going to be relative height. So because this electrical thing is kind of farther up in our visual field, that tells us that it's farther away than these two, right? Remember, stuff that appears higher in our visual field looks like it's farther away. Then the last one is going to be relative size. It's a little bit subtle here, but here's some comparison if you need it. So these electrical posts here are all slightly different sizes, as you can see by the comparison. So because this last one is smaller than this one, and this one is smaller than this one, this tells us that they're obviously farther away than each other. So using relative size to tell that there's depth. Okay, so some summary points. Remember that wavelengths of light are taken in by the eye and proceed to give us visual information. Different properties of those wavelengths determine the color and the brightness. The retina contains rods and cones. Each serve different purposes for vision. The 2 main theories of color vision are the trichromatic and component process theories. Remember those. And remember, we utilize a variety of different grouping techniques to interpret visual stimuli. And remember, we use both binocular and monocular cues to help us interpret our environment and determine depth.